There everybody, and welcome to this short video on section 5.3, the title of which is Review of Proof Techniques. So the purpose of this section, which is very short, is just to pause and quickly review the three proof techniques we've looked at so far. It is, of course, often a good idea just to pause and reflect on the stuff we've learned. It gives us extra time to process things. And so I'm just going to walk you through example 5.18 and then ask you to do a similar one to that example. Okay, so example 5.18 asks you to prove this. Let x be any non-zero real number. If x plus 1 over x is less than 2, then x must be negative. So we have three proof techniques: direct, contrapositive, and contradiction. Let's walk through each of them in turn. So here's what a direct proof looks like. We assume what comes right after the if. Right? That's what we've done many times. So we get to assume this inequality, and then our goal is to prove that x must be negative. So let's see if we can do that. So here, if you assume this inequality, this gives you something to sort of play around with. You can mess with this equation. So you now know that x is less than 2 minus 1 over x, things like that. Okay, so since x is not 0, we know this. We know x squared is positive. And therefore, we can multiply this equation through by x squared. So let's do that. We multiply everything in sight by x squared. That would then give you this inequality here, which after the simplification gives you this. Okay, and so now we can ask ourselves, well, is this any use? Where does this get us? And it gets us somewhere because you can factor out an x. So let's see that. It's also worth noting that you should always in your proofs mark this somewhere. If you're going to multiply an inequality by something and keep the inequality symbol going the same way, you need to mark down where you've done that and justify that. So I did it here and here for emphasis. Okay, now this inequality we can factor out an x, and then we end up with this, that x times something squared is negative. Now something squared is never negative. So if you're going to do something times something non-negative and get something negative, there's only one conclusion, that x itself must be negative. Okay, so just to quickly walk through this proof again, we're allowed to start with this inequality. Since we're allowed to assume x is non-zero, it says it right there, we can multiply this inequality through by x squared, by x to the third, anything like that, and we don't reverse the inequality sign. We end up with this inequality, and then from here we can factor out an x, and we learn that x times something non-negative must be negative. The only way for that to happen is if x is negative. So here is a direct proof of this result. I partially wanted to show you this just because there is some creativity involved here. So, thinking to multiply both sides by x squared, that might take some scratch work. When you look at something like this, the original inequality, you see this 1 over x, and you might say to yourself, oh, well, that 1 over x, that's pretty obnoxious. So maybe you multiply both sides by x instead of x squared. If you multiply both sides of the inequality by x, at least you get rid of this 1 over x, and then you would have x squared plus x is less than 2. And so maybe you could prove that x squared plus x is less than 2. But if you slap an x squared on here, and then you're allowed to factor out an x, that's better because you really want to learn something about x itself. So that can lead you to noticing, oh, if I multiply through by an x, I don't really get any information about x itself in a way that I would if I multiply through by x squared and land myself here. So that's a non-trivial thing to think of. So this proof is shown to you, as they all are, very clean, sort of just expressed, like, well, do this, then do this, then do this, and you're done. But it does take some creativity to think of something like this. So there's some scratch work and some thought and creativity involved in being able to produce a proof like this. But at any rate, here is another example of a direct proof. So now let's do the same thing with proof by contrapositive. So we have to assume not q. So x is not less than 0, so we assume x is at least 0. That's the opposite. And now we have to start from here and convince ourselves that not that is true. We have to convince ourselves that x plus 1 over x is 2 or bigger. Okay, so it's again worth pointing out that x is not 0. We already know that, right? So if x is bigger than or equal to 0, and x is not 0, then x is positive, and we can multiply inequalities by it, and we know what will happen. Okay, so here, I've just gone ahead and said, like, well, if this is my goal, this inequality here, I'll just do a chain of biconditionals here, a chain of if and only ifs. So this here is equivalent to, and now I can just multiply through by x. I multiply through by x, and I get this. That inequality is equivalent to this. X squared minus 2x plus 1 is 0 or bigger, which is like that. So here, the contrapositive maybe is better because we didn't have to think about like multiplying by an x squared to get what we want. We just multiplied by an x, which is a very natural thing to do to clear this denominator, and we get what we want that way. As always, you just have to be careful the way you write this. You don't want to say this implies this, implies this, implies this, and be done, because you're assuming what you are trying to prove if you do that. But anyway, this inequality is equivalent to this one, and so we're done. Okay, so this proof here, if you tried it direct and you got stuck because you multiplied through by x and then didn't know where to go with it, in general, unless you are instructed to, you can use whatever proof technique you want. So if you tried a direct proof here and got stuck because you couldn't think of this x squared little trick, you could always do contrapositive. That turned out to be easier, I think. Finally, let's do a proof by contradiction. So now we have to assume to the contrary P and not Q. So suppose there is some x satisfying the first inequality, but doing the opposite of what we want. You know, it could be 0 or bigger. So here, proof by contradiction maybe also is better than direct proof on some level because you get to assume two things. Well, I guess you assume three things because we already know x is not 0. So you get to assume that x plus 1 over x is less than 2, and you get that x is bigger than 0. So having two things to work with maybe is better. Okay, so like before, if x is positive, we can multiply by it. And we have this equation going already, inequality, going already. Multiply through by x, we get this inequality, which would then imply the x, I mean, this is if and only if, but here you don't have to be careful with that because you're allowed to assume this inequality here. You can assume this. X plus 1 over x is less than 2. So from that, we learn that x squared plus 1 is less than 2x. From that, we learn eventually that x minus 1 quantity squared is negative. That's a contradiction. Nothing squared is negative. There's no real number squared that's negative. And so here, one reason I wanted to show you this is here's another example where we reach a contradiction that's kind of external to the proof. Like we didn't explicitly contradict that, that x is 0 or bigger or something, right? We didn't explicitly contradict this. Like we didn't explicitly say, oh, it turns out that x plus 1 over x is bigger than 2 or something like that. No, we just eventually reached a place, reductio ad absurdum style, where we got something that just can't be true. So we assumed to the contrary not this, and as a consequence, we ended up learning that something squared was negative. Bad, can't do that. So here's a proof by contradiction of that same theorem. Okay, so just another kind of like example in the bank. So now what you should do is try this. This is exercise 5.37 in the book. Prove that if x minus 2 over x is bigger than 1, then x must be bigger than 2, using each of the three proof techniques. If you get stuck, the answer's in the back. As you might imagine, it is similar to this, has the same flavor, right? So I would try to, I would use some of this to try doing it. But anyway, try your hand at that. If you get stuck, you can check the answer, or of course you can email me. I'm always happy to communicate over email. We can also, of course, chat when I get back.